En ik krijg een environment aan het laden. Muziek is niet of niet.
Dat had ik ook. Dan staat hij, bij mij werkt het dan wel gewoon.
Maar het is nog steeds anders. Het is weer een ander ding. Nog steeds 3 jaar van 2 kanonnen. Nee.
Heb je hotpink? Hotpink is ook eens een hotpink.
Dit vast wel iets anders.
Ik ben een Brady.
Yeah, but this is already in Turkey. Yeah, but if you want to put ID.
Oh, maar dan is het
Dan kun je een soort van bij afbeeldingen kijken, want dan krijg je meestal ook een soort van. Als je dan bij afbeelding kan je bijvoorbeeld zien van. Many colors. Oh, hier. Maar
Die code wij van wie je doet dat niet.
Many colors. Waar komt het uit? Dat kan ik gewoon in één keer inpakken.
En niet of erbij.
Doet hij een veel?
Oh ja, wel. Er zit hem weer tussen. Dus in plaats van black. Een van die. Ook aan de andere kant. Het is niet de naam voor eronder, zeg maar.
Ja, ik kan van 360 aan 4 dan kan je gewoon een VR-bril met de college
moet toch ook
kijken.
gewoon de juiste camera voor hebben. Dan moet je ook niet
Ja, maar ja, dan zie je letterlijk, als je dan in VR kijkt, zie je gewoon een plat scherm, maar je kan wel om je heen kijken. Je ziet het
ja, klopt.
Dat zou wel echt grappig zijn. Ik kwam er laatst nog wel bijvoorbeeld aan het kijken op de telefoon en boven de telefoon en dan van, waarom kan ik geen video kijken? Maar dat was ook nog met 360 graden verwoord. Dus ik was echt zo.
Wat wil je?
Mijn environment is gewoon gebeukt. Ik heb nog niet opgestart en dan heb ik weer niet. En dan geeft het de eerste keer dat ik de kandidaat op nood geeft, die
Over hier, maar het is moeilijk. Over de rainbow column.
En dan loopt mijn environment.
Maar dat is een data.df. Exocol. Exocol voor mij. Oh hier, Hexacol is. Dat gaat er niet lukken. Babbelt. Misschien het lichtopvang aan de...
Ja, dat ben je. Het is toch echt niet uitgesproken. Rose elasticity. Die heeft ooit dat woord bedacht. Dat in die subtitel dat. Elasticity. Elasticity.
Maar dat is ook
Homo's de best.
Ja, je hebt ook een eten. Nee, er zit nog een Scadacity, want er zit nog een letter tussen.
Ja, ik spreek het wel.
Het is Scadacity.
Dat is van Engels. En hoe heet het? Die maar kut wel eens die hele kut. Ja, waar je echt 4 dingen niet uitspreekt.
Oh, the lion, the wardrobe and the necessity of the bitch.
Ja, dat zou best kunnen.
Impossible English. Ja, dat is
Ja,
dat is
that bitch.
de
Audacity.
en gewoon de line, de wardrobe is de audacity of this bitch. Of this bitch.
Dat is een Wales. Ja, daar weet je dan.
Maak anders de eerste en de laatste in ieder geval.
Maar als ik tegen jou zeg, de plaats Loughborough, hoe zou je dat spellen? Loughborough.
Een einde.
Best wel een leuke uitspraak.
Oh, dus het zeg maar je kent gewoon het.
Ja, maar dat is zeg maar voor hun rol in ieder geval. Omdat het al direct
Dit, en dan zeg je Loughborough.
Like the witch en de open.
Hij snapt het ook.
Het is zo vaak zo geschreven door Nederlanders.
Google this review.
Ja, meestal
Google this review.
ja.
Yeah, but the thing is, we're both
Dus,
and they're like after, so it's not like
het is heel makkelijk.
Maar we willen Engels.
Ja.
Zijn jullie net hiervoor dat het makkelijk was?
Pardon?
Zijn jullie net hiervoor dat het makkelijk was?
Nee, het ging
Maak
niet
het
over
moeilijk
dit.
maken.
Ik vind het niveau vind ik goed.
Niveau.
Het was te doen.
Het was er maar omdat we alle code al wisten. Dus dan,
En omdat we die vorige week ook al Dianova hadden.
Ja,
Daar leek het wel veel op.
als je die stap skipt,
er zijn
dan...
eigenlijk in stapjes gekomen.
Ja.
Ja. Nou gaan we weer een stap doen.
Uiteraard.
Uiteindelijk is het heel voor bedoeld.
Okay, people that are following this lecture online, can you type in the YouTube chat if you can hear me? Oh, no response.
No one there.
Everyone's sleeping. Oh yeah, you can hear. Ah, they hear me. Yeah. Okay. Thank you. So it means it works. It's always a little bit improvisation. Sorry. No. I put down the screen because otherwise I cannot use the whiteboard, the blackboard. This is already, not in the right construction sense. Okay, in the first 2 hours, there was someone noted. It's nice that you show all these diagnostics, but what if these diagnostics are not correct in the sense that the assumptions that you want to check are not the assumptions of the data model. But then we have to resort to something called data transformation. That's one of the solutions that you can do. But first, of course, you have to understand what actually the things that you should see. So for instance, here you see different plots of the residual. The first one here is a distribution of the residual. Now, if you look at that distribution, would you agree with me that that would not be normally distributed probably? We have to test that, but probably is not normally distributed. Why? Because it's not symmetrical. It is skewed to one side. It has a longer tail on one side than on the other side. It means it has more probability here than here. It slowly goes down here. If we look at the QQ plot, the next plot, and of course later on in the lecture I will zoom into this, we can clearly see that it does not follow that nice straight line, but it is so much as a sort of a curve, a banana that lies on that line. Yeah, it's a clear deviation from that straight line. And the point that I want to make, and this is just a continuous plot of that one, the point that I want to make is that seeing this will give you information that that the distribution is distributed as such. So we can infer from the QQ plot what we should expect for the distribution of the residuals. Here you see another plot that I still need explanation. That will tell us something what we could do to transform our data in such a way that this curve would be a straight line again and would fit with the straight line again. That's the idea. Yeah? So we will see how to identify the deviances, and we will see how some of them can be solved. And next week we will use more advanced methods, because these transformations that we do are actually will help you to do the statistics, but the interpretation of your data, because you did a transformation, will become more awkward, as we will see. Okay, heteroscedasticity. That was the first thing that we normally test. Let's see how that would work. Here is a situation of the fruit fly, from the fruit fly assignment that you still have to do because it's an ANCOVA assignment, and I already explained to you that it doesn't really matter if it's ANCOVA or it is ANOVA or factorial ANOVA, diagnostics will be similar. So here we see, I have to do it here because otherwise people online will not understand it. Here we see the factor, and here we see a numerical result, and here we see the combination. Now, here you see the fitted values. So if the values that are fitted, the expectation values becomes larger, we see an increase in variance. This is clearly not homoscedasticity. This is a clear example of heteroscedasticity. Yeah? You see with the increase of the fitted values, or here the increase of the thorax length, you see an increase in variance. That's a typical type of heteroscedasticity that we observe. This type of heteroscedasticity we observe, for instance, with the Poisson distribution. If it's not normally distributed, but Poisson distributed in some cases. Okay, nice, we have identified it. What now? What can we do? Here I just zoom in to make it a little bit more clear. Here you see a few points with only a few, little bit of variance. And here you see many points with a lot of variance. I will return to this, why there are more points here than here. It has nothing to do with this heteroscedasticity, but I will return to that later. Okay, so we have to deal with this, clearly. Because if we do the numerical test, non-constant variance test, it's clear that now we got a significant difference. So we detected heteroscedasticity. Yeah? We rejected the null hypothesis of homoscedasticity. Yeah? By rejecting it, we have detected in our data heteroscedasticity. Yeah? Now there's another thing that we test here. If the relation is linear, and these p-values will tell us that it was linear. Tomorrow more about that in the lecture of Frans. Now what could be the reason? Now we always assume, and now I only concentrate on thorax length, but I could also do it on the other one. We always assume that thorax length would be independently measured from the residuals. So we can estimate them independently. That's why we can say the plus sign. Yeah? But that's not always the case. Clearly, if we look at this plot, the residuals is a function of the thorax length, or at least one of the model outcomes. So it means we probably are in some sort of this situation. Maybe there is a factor there that might increase or decrease the strength. Now, basically this means that there is a slope of 1, more or less. Yeah? But the idea is that we have a multiplication here. Okay, that is clear. This multiplication can lead to this. So how can we solve it? By recognizing it, if you have a multiplication and you take the log of it, so if I take a log of this one, of x times y, then I can also write it as the log of x plus the log of y. Yeah? So I get this plus again. So let us do it with log longevity, that's log longevity, as a function of log thorax length, because basically you do it on both sides. Then you get here log thorax length because longevity is basically this, yeah, this is what we want to fit. This means that we get log thorax plus log residuals. So we have our problem solved if the source would be indeed this case. Yeah. So is this cheating? Is this cheating? Is this a form of fraud? No, because the log transformation is a continuous transformation. Basically what it does, if you have a certain distribution, like the long tail, as we will see, could be something like this. What the log transformation will do, it just pushes harder on this side, and as a result, after log transformation, these data are compressed more than these data, and as a result, we get this symmetry again. Of course, we have to test that. That is an hypothesis. Let's see. Now, here we have done it. Here we have the log longevity, and all the rest stays the same. There's no log here. Yeah. Here's just longevity. It's on the fruit fly, and I looked at the residual plot, and this is the result of the residual plot. And now we can clearly see that they are more homoscedasticity is back. Now I want to make a note here. So in the beginning I thought this is not maybe really the best data set to show, but this also shows something else. If you do data, you want actually to get in your design such a way that you get similar number of data points in this region as in this region. Yeah? Because it might well be that the effect that we observed is due that we have here only a few points. Yeah? But at least we see here that visually it looks better. It would be much better if we had here more points. So that's one of the reasons, if you do experimental design, try to figure out that you get similar number of observations at similar values that you measure. Yeah? Or different values that you measure. That's not always possible if you are, for instance, in the field. But if you're not in the field, you should try to accommodate that. Now, of course, we can do a test again. And here we do a test. And now we see that the p-value is markedly greater than 0.05. Resulting in our saying we did not detect any deviation from the assumption of homoscedasticity. Yeah, homogeneity of the variance. It also, yes?
Right now it went like a cone, right?
Yeah.
What if it went the other way around?
Yeah, I will come to that.
Oh,
Yeah. So you can imagine the question here is, we showed here one situation, but what if it is the other way around? So if you start with a long tail and then it drops. Yeah, then you have to do something else. Then the log transformation clearly does not work. But I will come to that. Yeah. And it can be even more complicated, and then a transformation will not work. So for instance, that would be something like this. A sort of a flowing, let's draw it. So assume that you would get something like this. You know, that's not a simple transformation that would get something like this. Probably you will have still a factor that is not in your model. So you have to be careful with transformation that you don't want to transformate out effects that should be explained by, say, a factor or some other variable. Yeah? Or it might be that there is an outlier. You should not try to transform out an outlier, because an outlier is something that you don't want to have in your data anyway. So this is why we first run through the whole diagnostic set. So we do first test for heteroscedasticity. Oh, that's a problem. Then we test for, is it normally distributed? Oh, maybe not a problem. Then we test, is there an outlier? Oh, no outliers? Okay, then we can think about transforming. Yeah? And then, yeah, as we will see. Yeah? Now here is the diagnostics of the plot of the log transformed data set. And there you see that it's much better. And of course the test showed that we did not found any heteroscedasticity. So that's nice. Then we can look if we do a log transformation, that might affect our QQ plot. That might affect our residuals. Now, if you look very carefully, this is our original one, and this is the one. And this is the one with the log transformation. They're not exactly similar. There's a small difference, and it will be clear what the reason for that is in the second part of this lecture. Here you see that if in non-transformed, there is a deviation from the line upwards, positive to the solid line. After the log transformation, you see that this has changed to under, negatively, to the solid line. Yeah? So it turns out that log transformation, one way or another, has changed this part from here to here. It did not affect so much this area, only that in this area the points are more, stretched out a little bit. Yeah? So the log transformation did something, but did not affect so much the assumption of normal distributed residuals. In this case, it would be okay. Maybe in another case, it would not be okay. So we always have to check that. The same thing with the outliers. This is our original model. What do we see here? Here we see the Cook's distance again. The Cook's distance is a combination of how much data point deviates from my model. So how big an observation is in terms of being a residual, its size, literally, and how influential that point is. Now you see here that this one and this one, they deviate quite a lot, the most of all. But because they have small influence, if they have small influence, the combination of these two, I get a small, relatively small, Cook's distance. This one, however, it has some deviance from the expected value. It's not that big compared to 75, but it is influential. And then you see that this one will increase 75. So the Cook's distance is basically a value, how far away does it deviate from the expected value, which is a characteristic of an extreme value or an outlier. And of course, when it becomes also influential, in the sense that it might affect my statistics, the estimate of the slope, for instance, then the Cook's distance will also rise. So Cook's distance is a combination of these two. Now, as I told you in the beginning, there is no effect. We don't worry if the Cook's distance is smaller than 0.5. Clearly, if we look at the axis, it's not the case. Yeah. So we can say we did not detect any outliers. Of course, you can also do the outlier test. Then in the head values, there is a rule, the blue dashed line. I have to program that in myself, so that normally you don't see that. The blue dashed line is 2.5 times the average head value. And if an observation is bigger than 2.5 times the average head value, it means that it has a higher influence. It has a significantly higher influence. So how can we understand that? Now, it's difficult to understand with a factorial ANOVA, but it's rather easy to understand when we do linear regression. Even a simple linear regression doesn't have to be the topic of tomorrow, where there's also a linear regression. What we have is this situation. We have a few points, and I fit a line through it, and I fit the line through it in such a way that would minimize the sum of squares. So basically, would minimize the size of every individual point to this line. Similar to taking a mean, basically. Yeah? So this is also an estimate, just as the estimate is when you take a mean. Okay, what will happen if I have an observation here, which might be considered an extreme point or an outlier? What will happen is that my line will just go a little bit down. so that this difference here is more or less similar to the difference of all these points to this new line. Yeah? So basically start to compensate. Now imagine if I have a lot of observations, then this effect will just be averaged out. Yeah? Because the adaptation of this line to go down will be, you know, will be worked against by the number of observations that you have here. Yeah? Because you want to minimize the total distance, it means that this effect becomes less influential every time we add new observations that behave like a normal observation. Yeah? Now imagine that we have a new point, but it's not in the middle. So if I do it in the middle, then the only thing that might change might be the intercept. But if I do it a little bit further away, like here, yeah, what I can get then is that I get something like this. Yeah? So it means now, not only do I get a much bigger, intercept, but I also get a different slope. So this point, by, you know, just this position in this problem, data problem, this point here, or this point here, or here, all the points that are in the extreme, they have a higher influence. Yeah? And actually, it's also what you see here, because they are ordered by this numerical value, you see this behavior. Yeah? So it's from lower concentration to higher concentration, or in this case, thorax length. That has to do with that. Yeah? So this is, means that these will be very influential. Now look at the following more extreme situation, where we have a clear outlier. You have here several points. So you want to draw a line like this, but then you have here a point. What will happen? This point will have a low value on this location, yeah, because it does not deviate from the point as much, because these points here also deviates a lot now. So I will not recognize it in terms of here. I will, however, recognize it in terms of its influence as a head value. But the combination of the two can make the Cook's distance smaller than 0.5. So it's clear that this would be an outlier, but its influence is so big that it totally dominates the statistics, and then you will not recognize it as in the Cook's distance. So that's why we put all these three together. Or, I have to stay here, or there's a big deviation here, that it's far away from the expected value, or it has a high influence, and then they have a high Cook's distance, or the influence is so high that, you know, the Cook's distance is low, but then we have to see it here with the head value. Yeah? Okay, we will return to that several times because there are many combinations to digest, but I hope to illustrate that it's not always easy to look at this, that we always combine it with another visualization. Normally, of course, this type of outlier we would have already have extracted in the first step of the analysis, where we did the summary of the data and the first plot. Then this type of outliers you probably already have recognized. Mm. That's the importance also of the first step that we do. Okay, yeah. Okay, now this is the situation of the log transform model. Now here we see that 75 has become more influential. Bigger an outlier, and it was already influential because it was more at the extremes. Therefore, it got a higher Cook's distance. Let's go back. Here it goes to 0.06, and here we are at 0.3, still below the 0.5, so we don't need to worry. But it's clear that after the log transformation, this can have a different effect. Note that the head value is not affected. So the influence is not affected. It's really how far it deviates. Yeah? This will become clearer when we talk about GLM next week, why this could be the case. Now look at these ANOVA tables. Here we have the model without the log, here the model with the log transformation. Now look at the sum of squares here, and look at the sum of squares here. The last one are really, really smaller. Can we understand that? Yes, because we took the log. It will decrease the size, the numbers, therefore it will also decrease the variance. Makes sense. Of course, in the end, we do see a little bit different f values, because these f values are scaled at the end, because you divide by these two, by the residuals. So this value here is this value divided by the residual degree, mean square, and this value is this value divided by this one, and this one is this value divided by that one. Same thing as here, so we normalize always to the residual. So that's why we can compare the f a little bit better. But you see that the f values here are bigger, therefore the p values are also smaller. Here you see that this is the smallest number that it can print. Here it was not there, but now it's become smaller. Here we see this value is also bigger. We see that the p value has also become smaller. Yeah? So
Dat had ik al bedacht.
that's a very good response. For the people that doesn't speak Dutch, it says, I also thought that. Yeah? And for the people online, I don't know if you hear it, but there was a remark from a mobile phone, which was actually quite good at this moment. Okay. Yeah, so it has an effect on your statistics, of course. But the only thing is, of course, below, there the assumptions of homoscedasticity is correct. The previous one, the upper one, yeah, has the problem of heteroscedasticity, so we cannot trust the statistics. So this looks cool, this looks nice, no problems.
Wait, what did you say? What's the difference in, because isn't the results the same for both of the models actually?
Well, actually the result in terms of hypothesis is the same.
Okay,
Yes. That doesn't necessarily have to be so. Yeah, it could be, for instance, that you see that this p-value already gets smaller.
Yeah.
Now, assume that this would always that there is an effect, but it was not detected under the condition of no log transformation. You might detect it here. Yeah, and the reason for that is that this assumption of heteroscedasticity makes it more powerful. Homoscedasticity makes it more powerful. Now we can also look at the regression table. We did not discuss the regression table, but in the regression table it's similar to the post hoc test. There you get all the estimates. So for instance, here you have the estimates of the different intercepts. This is an estimate of a slope. Here you have the difference of the estimates of the different slopes compared to this slope. Will be discussed tomorrow in greater detail, but the point that I want to make here are the numbers. These are clear numerical numbers. They have something to do, in this case, with longevity. Yeah? So the expected longevity of the fruit fly under different conditions. Here we did the log transformation, and now these are not longevity anymore. They are log longevity. So, does any one of you know what log longevity means? Why would you take the log of longevity? Why did you take the log of something that just measures how long an individual lives? Could there be a good reason for that? I don't know it. Maybe you know, but I don't know it. Yeah? So I did a transformation motivated by my data, but as a result, I get estimates that I cannot give direct interpretation to. I still can use the p-value, so I can say if there is a significant effect of certain treatments on longevity, but these estimates here does not make any sense. So I did the log, and if you want to use the log of the exponential, you cannot go from one to the other. It's totally different. It's a new fit, so it's not easy to bring these values back to the other values. You cannot back transform easily. Yeah? And this is one of the reasons why transformation, sometimes you have to use it, but you use it for the test statistics. For the interpretation, yeah, you have to find another strategy to deal with that. Yeah? Now, next week, when we talk GLM, that will be solved for us, because we actually know what is happening. Now, this is the new plot with the log transformation. And you see here different lines, so we have to deal with Rankova, the topic of tomorrow. And you could say, well, indeed, there are different slopes, but probably these slopes are not significantly different enough. That's why we get in the ANOVA here that they are not significant, the interaction. Yeah, but more about that tomorrow. Okay, that was about heteroscedasticity. Now, the second step that we normally do is, are the residuals normally distributed? The thing that we started with in the title page of this lecture. Here we will look at one type of transformation, which is just where the log transformation is just a special case, and that is the power transformation. Yeah. So if we take longevity, or for instance, what we can blood pressure of, well, we already took the log of the log expression in the lecture of this morning. And if we take it to the power 0, then we have a log. We take the log. It's a limiting function. So if we take a power to the -1, so lambda to the -1, then we get 1 divided by lambda. Or blood pressure by the -1, we get 1 divided by blood pressure. Yeah? If we have blood pressure to the 0th, if you think about this, this becomes very weird. Yeah? Then it turns out that it's best in the limit that is really 0, it becomes log blood pressure. That's basically the one that we used in the previous example to deal with the heteroscedasticity. Yeah? Then you have, of course, blood pressure to a half, which is the square root of blood pressure. So these are the power transformations. If this is a third, then you get the cube root. Then if you don't need the power transformation, it's just 1, power of 1. And then of course, you could have all sort of other combinations. This is the square, or you can have the square with 2/3, for instance. Yeah, these are all transformations that can be done. Now, the log transformation, the use of that might be clear. For instance, in the case of the expression data, when we look at the log, because we looked at the ratio of genes before and after, then we can look at the overexpression or under expression. Then log transformation makes sense, because we know when log is 1, nothing happened. There's no over or under expression. So sometimes these transformations can make sense in the context of your research. Yeah? So now we have to decide which one of these to choose. That can be done what is called the Box-Cox transformation, and if you run this function, it will suggest to you, so this is the model that I investigating, it will suggest to you a transformation. Actually, this is also the fruit fly data. Now, running this, you see that 0 is just in the confidence interval here. This is the real estimate, this is the confidence interval. So I could do a log transformation, but I could do also 1/3, the cube root of longevity in this case. Yeah, if I would want to do it on that one. But of course, there was heteroscedasticity, but normally this can also be used for if it's not normally distributed. Yeah. Okay. So we return to the QQ plot then, because it's the QQ plot where we test if something is normally distributed. So here I draw a normal distribution, and the horizontal lines are the two percentile quantiles. So between every two lines is 2% of my total probability. And it's clear that these lines, they become further away from each other as the density of probability will go down. Yeah? Okay. Now the importance is that I know the locations, the coordinates on this line, the coordinates of these points, of these lines that put to the border of the two percentiles. Now I do the same thing for the log transformed data set, or a distribution that has a long tail. It does not really have to be a log normal distribution, but a distribution that has a long tail on one side. Clearly the coordinates of these points and how they are from small and then they become bigger, whereas here there's a clear symmetry in the middle. Here they become bigger, and on that side they become bigger. Yeah. If I do that in a QQ plot, so this one, I plot this one, the quantiles against this one, I get this. So when I observe something like this, here it's above the line, a little bit below the line, and then above the line again. This curvature, then I know, okay, this is what I can expect. Then I think, okay, this means that a log transform might be a good idea, or a square root transform might be a good idea, because that will push these numbers more. This will reduce the size of these numbers more, make them smaller, more smaller than these numbers, and I will get a normal distribution again. Yeah? So here's the QQ plot, and you see it's exactly the same. This plot and this plot are exactly the same. Yeah? So this is the QQ plot as we normally use it from the car package. And again, this is of course interesting, because if you had done the Shapiro test, which will only give you the p-value, you cannot infer from that p-value what type of distribution that would be. That's why we combine always statistics together with visualizations, in this case QQ plot. Now let's look at some different distributions. For instance, your question about different distribution. Here you have the distribution you suggested. Yeah? So now we have a long tail on the left side. Yeah? So it's a long tail here, and then it drops. We get the mirror image of the other one. It's a mirror image of this one. So if I see that it starts low, and here also, then it means that we have a thing like this. We see that the QQ plot now of the Cox box transformation is not suggesting a log transformation, but it goes in the other direction. It says, okay, you can do a cube, yeah, a cube or 2.3, but normally we use whole numbers. You can use after the comma, but that's then you have to deal with total different type of theories. Here we have a nice symmetrical one. Note that there is a little bit lower elements here and higher elements there. I will return to that. Here we have the one that we just discussed, where we need a log transformation or a power somewhere between 0 and the log, dus between 0 and 1. And we can do that with a log transformation or a cube or a square root. Yeah, you see it is also suggested here to do a log transformation. Of course, we can go further, even a longer tail, and here a longer tail, and here even steeper. Then here you see this thing going flat almost. Then we are in the range of negative values, and then you get something like this. So this one is, say, -1/2. So it means -1/2 would mean 1 divided by the square root of the blood pressure. Yeah? Or 1/3, then this. Now, something that you would observe quite a lot if you do your data, and actually when your data is normally distributed. If you do your QQ plot, and you get a straight line here, you find something like this. So it goes up here and down here. What type of distribution would that be? Difficult, because this, you see this for the first time. And I will explain why it's not so strange that you might observe that. First of all, the situation here is of a distribution that has a longer tails. So if this is a normal distribution, that one would be something like this. A little bit more probability in the tails. There's one distribution you know of which has that property, and it is the t distribution. Yeah? T distribution for smaller degrees of freedom will have what we call a fatter tail. It means that the exponential decrease here is actually less than an exponential decrease, and then you get these taller tails. For biology, if you don't look at test statistics, but in biology, in most cases, if you look at distributions of systems, you expect these tall tails, because that is related to some complex interaction that's going on. Yeah? But we will not go into it here. Now, why would we expect that? Well, if you have such a distribution of a data, so you collect data, these will all be nice, some will be here. But then, to a certain point, if you have a little bit more extreme values that are not outliers, but just extreme values, a person of 2 meters 30 or 1 meter 10, they are relatively extreme in this population, but they belong to this population. They will go down here because it will give more fatter tails. You will observe here a few of these more extreme ones. So if you have more extreme values, which can happen, then you will see them going up here or going down there, because that will result in these fatter tails. Because if we will fit the data, then because to accommodate these observations, we will automatically give them a little bit more space there, or probability. Yeah. So this is not so bad. If you get something like this, even if they are outside this dashed line, yeah, even if they are outside this dashed line, and you have seen that there are some more extreme values, but there is not such a nice continuous structure like that, then you can say, okay, then probably this is due to a little bit more extreme values, but not outliers. Extreme values that we might expect, maybe with low probability. Yeah? Now there are some more transformations that you can do. Look at this one, the minus sign and then the square root of the response. When do you use something like that? For instance, if there is a maximum of a value. For instance, if you look at a leaf and you want to see what the effect of a pest is on the leaf, and you want to say how much of the leaf is being destroyed or being eaten, then the maximum number of surface area is 100%, and the minimum is 0. Yeah. So it means that the value can only be between two values. And then it turns out that this transformation works quite well. Then the below one has the same thing, has the same property, that there is a maximum and a minimum, and that will be related to the binomial distribution, and that will be discussed again next week. Then this transformation is done within the algorithm that we will use to fit our models. Yeah, because then we actually start fitting as a response variable a factor instead of a numerical value. Okay. So here you see an example of a generalized linear model that we do next week. Note the similarity. Normally we do GLM, LM, and then this part. Now we generalize it. We do the same part, but we have to say where we generalize it to. So we say next week again everything the same, little bit difference, but we can deal with these type of data. Then we will discuss this also, and this is basically I put them all together. Oh, here this is something different. Here, for instance, I did another transformation. Here I do a cube transformation, cube root transformation of the longevity, and here I do a cube transformation of thorax. Yeah. So here I do the inverse of here, this one. So now I start modeling basically the response variable of the explanatory variable, and here I do the response variable, because this is a question that we often get. Why not take the other side? Why not transform, for instance, the treatment or gender, or in this case thorax? Why not that one? And then you can keep longevity in the same dimensions that you're interested in. Well, that will not work if we have these problems. And we can see it here. Here we have the cube of the thorax. Then we still see that we have this enormous heteroscedasticity. And if we do it from the longevity, it works fine. Yeah? And we can understand that because the thorax length does not contain the residuals. It's just one part of our model. But the longevity, the response variables, also contains all the information of the residuals. Therefore, it makes sense to transform that one. Yeah? Okay. So, what's next? Apply theoretical rationalizations. For instance, in some cases, it's wise to transform the explanatory variable because you know that that makes sense. For instance, we see that a lot when we talk about a dose of a certain concentration. In many cases, that can be also log transformed for many reasons. That in some of the data you will get, you see log dose, for instance. The other ones we will discuss on Monday, 21st of February, is another method to deal with it, so that we can actually give an interpretation to our statistics. We could now not give an interpretation to our statistics of the slope and the intercept, because the dimensions of log longevity, for instance, of log blood pressure, we don't have any conceptual interpretation of that. But with GLMs, we can actually do that. We can give an interpretation to the slope. We can give an interpretation to the intercept in the context of our research. And the last one, GLS, generalized least square, is a method explicitly designed to deal with heteroscedasticity, but that will not be discussed in this course. We don't have time for that. But the principles are all the same. Again, that's one of the assignments that I gave you for this whole course, is to recognize which parts of the course are always the same. Which part do we always reiterate? Things like variance, means, expectation values, degrees of freedom, the diagnostics, interpretation of the F statistics, T statistics in terms of p-values, always the same steps. Only the models, the context becomes more complicated. If I would use another method, GLS, your assignment then would be, okay, do I understand that in the context of the first week? And if you do that, you understand GLS. And if you do that, you know how to do that analysis. We tried this the level that we want you to have at the end of this course. Okay. I got a question here. From which of these plots can you derive what the power is, and could you re-explain how to interpretation of the box cogs? Okay, so the interpretation of the power you get from this plot, the box cogs plot basically. So let's go back here. So you have to make a decision which one of them to use. So you have to make a decision on lambda because you want to take the variable to the lambda, power lambda. Yeah? So here, for instance, we see that there's an estimate here in this range of what the Box-Cox transformation would suggest you would use. So I would say 1/3. Maybe if I want to use a log for one reason, I could also just use the log transformation because that would be 0. Here you can see lambda 0 would be log. Or I could even do a square root, a half, that is here. So we get it from there. Yeah.
But how do you see that's a half? Like, I don't understand.
Okay, so here, this axis here, you don't see it, but this is lambda. This is the value of lambda.
But then the last, like, line,
This one?
that's not a half, that's more.
No, but that's the confidence interval. So basically it says all the values in this region, we consider statistically similar solutions. So I would guess this one at 1/3.
Yeah.
But a half is still in that range.
Okay.
0 on the border. Yeah, but still inside.
So then you choose which one of the two.
Yeah. And sometimes you take log because that makes more sense. Other times you use square root because cube root might be more complicated to give an interpretation to. But also with the GLMs, we will return to that problem. How to now we could do it here also. Say that you're not sure. Should I do a half or should I do a third? You can run both models and look at the size of your residuals. The smallest residuals will probably give the best fit. Yeah. So there's quite some information that we already got. Fundamental information like the size of the variance observed in the residual, which is just the sum of squares of that is just an estimate of how big the variability is in your residuals. Yeah. So that's a nice question. Okay. Slide 26. So if you want to know here what the transformation is, you should look at this part here. So it means that here the transformation would be somewhere, well, maybe 1 minus 0.3. So this one that I put here. Yeah, so you get it from this one. Yeah, this is just a visualization of it, which can give us information of what we might expect. Okay, there's another question from Rose, but Rose, I will answer that question in the end. Are there other questions here for now? No other questions? Okay, then Rose asked the questions, what can we do this afternoon? Well, most of you have done the first one and started already with the third one. So that's the tooth growth. The second one is the tooth growth. The third one is about fertilizer. And there you actually need to transform. Yeah? So in the afternoon you can work on that data set. And tomorrow morning, as if I remember it correctly, we again start with a lecture. So there's no room for, yeah. And then we will do, of course, the topic of tomorrow is ANCOVA, and you will do an assignment on ANCOVA, which will be very similar to the assignment that you did today. Yeah? Only the interpretation is a little bit different. Slopes in this case. Yeah? Patrick and me will be here until 4:30, because then I need to run, 3:30. Then I need to run for another meeting. Yeah? I think we can stay here, and of course we can sit everywhere where you want.
Waarom ging zie je meestal?
Ja, geen idee. Bij deze niet.
Altijd
Hij zie je, ik
Altijd
meestal maar
even.
ook. En daar staat het Vlaams.
All